Hello, I'm Sapna Davis of ECE Department, Rajagiri School of Engineering and Technology. I'm going to discuss about the basics of information theory. The figure shows the basic block diagram of a communication system. It consists of a source, transmitter, channel, receiver, and destination. The transmitter will be sending the information to the receiver via the channel. Next, we'll see what is information. The most significant feature of information is uncertainty or unpredictability. We'll see the example of a weather forecast of Delhi. There are three statements given. First one is the sun will rise. The probability of this event is 1. So we can say that it contains no information because there is no uncertainty. The second statement is it will rain. Its probability is 1 by 3. So it contains some information because it doesn't rain every day. The third statement is that there can be tornadoes. The probability is very less and it contains more information because tornadoes are very rare. The conclusion is that the amount of information increases when probability decreases. Next, we will see the definition of information. Consider a source that produces messages A and B with probabilities P of A and P of B. The amount of information associated with the event A is given by I of A equal to logarithm of 1 on P of A. Then the properties of information are, first one, the information cannot be negative. That is, I of A will be always greater than or equal to 0 because P of A lies in the range of 0 to 1. The second one is when we are sure about the occurrence of an event, no information is conveyed. That is, limit P of A tends to 1, I of A will be equal to 0. Third property, more information will be conveyed by a less probable message. That is, if P of A less than P of B, then I of A will be greater than I of B. Fourth property, when the events A and B are statistically independent, the compound messages C equal to AB has the information I of C equal to I of A plus I of B. Because P of C equal to P of AB equal to P of A into P of B. Then I of AB equal to log 1 by P of AB equal to I of A plus I of B. Fifth property, consider a source with the n equiprobable messages with the individual probability equal to 1 by n. Then the information associated with a single message is I equal to log 1 by P. And this will be equal to log n to the base 2 bits if the base of the logarithm is 2. Next, we will see the unit of information. The unit of information with the logarithmic base b equal to 2 is called as the binary unit or bit. The unit of information with the logarithmic base b equal to 3 is called a triples. For quaternary choice b equal to 4, the unit is quadruples. For a decimal choice b equal to 10, unit is a decids or heartless. For natural logarithm I equal to log 1 by p, Napier's or nats is used. Next topic is entropy. Consider a source emitting sequences of symbols from a fixed finite source alphabet S equal to S1, S2 up to SQ. There are q number of symbols. Such a source is called as a discrete source. If the symbols emitted are statistically independent, the source has no memory, and such sources are called as memoryless or zero memory sources. The probabilities of the emitted symbols are given by Px equal to P of S1, P of S2 up to P of SQ, and this can be also written as a P1, P2 up to PQ, where summation Pk will be equal to 1. Consider a long sequence of n symbols produced by a zero memory source. Let the sequence contain n1 number of S1, n2 number of S2, and so on to nq number of SQ. The amount of information associated with each symbol is I of Sk equal to log 1 by Pk, and this is called as the self-information. The total information conveyed is given by It equal to summation I of Sk into Nk bits. Then the average information conveyed is given by H equal to 1 by N times It. Replacing for IT and pk, we get h of s equal to summation pk log 1 by pk with step symbol. And hs is called as the entropy or average information of the source. Next is the properties of entropy. First one, the entropy function is continuous in each and every independent variable pk. Because pk lies in the interval 0 to 1, logarithm of a continuous function also will be continuous. The entropy function is a symmetrical function of its arguments. That is, h of pk1 minus pk equal to h of 1 minus pk. As long as the probabilities of the set are the same, it does not matter in which order they are arranged. Consider three sources S1, S2 and S3 with the probabilities as given below with the summation pk equal to 1. All sources will be having the same entropy, that is h of S1 equal to h of S2 equal to h of S3. Third one is the extremal property. Consider a zero memory source with a Q symbol alphabet S equal to S1 S2 up to SQ with probabilities P equal to P1 P2 up to PQ. We'll evaluate the expression for log Q minus Hs. Log Q is replaced as a summation Pk log Q and Hs equation is also replaced. Changing to natural logarithm and simplifying, finally, we get h of s will be less than or equal to log q. As a conclusion, for a zero memory source with a q symbol alphabet, the entropy is maximum if and only if all the source symbols are equiprobable. That is, h's maximum will be equal to log q. As an example, we'll consider zero memory binary source. Here the source alphabet consists of 0 and 1 with probabilities q and p, where q equal to 1 minus p because p plus q equal to 1. H's equation is also written, and if you're plotting h's versus p, we can see that when p equal to q equal to 1 by 2, h's is maximum and that is equal to 1. Fourth one is additive property. Suppose you are splitting the symbol SQ into m subsymbols such that SQ equal to union of SQJ and P of SQJ equal to PQJ and summation PQJ equal to PQ. We will evaluate the expression for H of S. Simplifying the equation, we get H of P1, P2, PQ minus 1, PQ1, PQ2 up to PQm will be greater than or equal to H of P1, P2, PQ. It means partitioning of the symbols into sub-symbols cannot decrease the entropy. Next topic is information rate. Information rate R is equal to RS times H bits per second, where RS is the symbol rate. The average symbol duration tau is given by summation pk tau k, where tau k is the duration of the gate symbol. Then RS will be equal to 1 by tau symbols per second. Next, we will see the extension of a zero memory source. Consider a binary source emitting symbols S1 and S2 with probabilities P1 and P2 such that P1 plus P2 equal to 1. The second extension of this source will have four symbols given by S1 S1 with probability P1 square, S1 S2 with probability P1 P2, S2 S1 with probability P2 P1, S2 S2 with probability P2 square. If we are summing these probabilities, we get P1 plus P2 the square, which will be equal to 1. Entropy of the second extension of the source is H of S square equal to 2 into Hs. That is the conclusion. The third extension of the source will have 8 symbols given by S1, S1, S1 with probability P1 cube, S1, S1, S2 with probability P1 square P2. Like this, we have to take all the 8 possibilities and multiply the respective probabilities. If we are summing all the probabilities, we get P1 plus P2 the cube, which is equal to 1. Entropy of the third extension of the source is H of S cube equal to 3 times H of S. In general, entropy of the nth extension of the source is H of Sn equal to n into H of S. Next is a joint probability matrix. A simple communication system is shown X is representing the set of transmitted symbols and Y is representing the set of received symbols. And the system can be characterized by the joint probability matrix P of xy, which is given here. Here x1, x2 up to xm will be representing the transmitted symbols and y1, y2 up to yn are representing the received symbols. Sum of all entries of a joint probability matrix equals 1, and also sum of all entries of a joint probability matrix in the kth row will be equal to P of xk. Similarly, sum of all entries of joint probability matrix in the jth column will be equal to P of yj, and summation P of xk equal to summation P of yj equal to 1. The communication network shown has 5 probability schemes Px, Py, Pxy, Px on y and Py on x, and accordingly we can define 5 entropy functions. Next is entropy functions. Hx is representing the average information per symbol transmitted. It is the source entropy. Similarly, Hy is the receiver entropy, that is, it is the average information received per symbol. H of xy is the average information per pair of transmitted and received symbols. H of x on y we can define next. Consider a symbol yj is received when the symbol xk is transmitted. The average entropy associated with this scheme when yj covers all the received symbols E of h of x on yj is the conditional entropy h of x on y or equivocation. It's a measure of information about the source when it is known that y is received. H of y on x is the measure of the information about the receiver and it is also called as the noise entropy. Joint entropy can be defined from the joint probability matrix and the source entropy can be defined from the source symbol probability set. Joint probability matrix also we can find the source entropy h of x and the receiver entropy h of y. And also from the Bayes theorem we can show that summation p of xk on yj equals 1. Taking the average of the entropy function h of x on yj, the equivocation h of x on y can be obtained. Similarly, we can write the expression for h of y on x. All the 5 entropies are interrelated. We can show that h of y on x equal to h of xy minus h of x. Hence, hxy equal to hx plus h of y on x. Similarly, h of xy equals h of y plus h of x on y. Next, we can find the expression for h of x minus h of x on y. Simplifying, we get h of x greater than or equal to h of x on y. Similarly, h of y will be greater than or equal to h of y on x. Equality holds if input and output symbols are statistically independent. Next topic is mutual information. H of x bits are needed to represent one input symbol on an average. If you observe the respective output symbol, we need only h of x on y bits to represent the input symbol. Observation of the output symbols provides us with the h of x minus h of x on y bits of information. This difference is called as the mutual information I of xy, which is given as h of x minus h of x on y. For a symbol xk, if p of xk is known, then p of xk on yj can be computed at the receiver side. The difference between the initial uncertainty of the source symbol xk, that is log 1 by p of x of k, and the final uncertainty of the same source after receiving yj, that is log 1 on p of xk on yj, is the information gained through the channel. Difference is known as the mutual information between the symbols xk and yj. Averaging over all xk and yj, we obtain the average information gain of the receiver ixy. We'll see the properties of mutual information next. First one is mutual information is symmetric with respect to its arguments. That is I of xk yj will be equal to I of yj xk, which can be proved as shown. The second one is I of xy equal to h of x minus h of x on y. And third one is I of xy equal to h of y minus h of y on x. Fourth one is I of xy equal to h of xy plus h of y minus h of xy. Fifth one, for a particular residual symbol yj, h of x minus h of x1 yj can be negative. But when all the output symbols are covered, the average mutual information is always non-negative. Entropy relations are shown next. Left circle is representing hx and the right circle is representing hy. Overlap between the two circles is the mutual information and the remaining portions represent the respective equivocations. So h of x on y equals h of x minus ixy and h of y on x equals h of y minus I of xy. So h of xy equal to h of x plus h of y minus ixy and also h of xy equal to h of x plus h of y on x and this is equal to h of y plus h of x on y. Next we will see the source encoding. Let a source be characterized by the symbols s equal to s1 s2 up to sq. This is the source alphabet and consider another set x comprising of r symbols x equal to x1 x2 up to xr. This is the code alphabet. Coding means it is the representation of every symbol of s by a sequence of the symbols of x with a one-to-one relationship. The sequence of symbols of x2 specify a source alphabet is called as the code word. The number of symbols in a code word is called as the word length. Next, we will see the definition of block codes. A particular source symbol is encoded into the same code word. The code can be of fixed length or variable length. For example, consider the source with the four symbols S1, S2, S3, S4 and the code alphabet consists of only 0 and 1. Then the code word set can be given by 0, 0, 0, 1, 0, 1, 1 corresponding to all the four symbols in the source alphabet. A block code is said to be non-singular if all the words of a code set C are distinct. A non-singular code is uniquely decodable if every word in a sequence of words can be uniquely identified. A uniquely decodable code is said to be instantaneous if the end of the code word is recognizable without inspecting successive code symbols. Instantaneous decoding is possible here. Examples of different classes of codes are given here. First one is a singular. You can see that the code words are not distinct. The second one is non-singular, but it is not uniquely decodable. Here the code words are different, but 0 is the first bit of 3 code words. Third one is uniquely decodable, but not instantaneous. Here for decoding, we have to wait for the successive code word to arrive. And the last one is instantaneous because instantaneous decoding is possible. Prefix property. A necessary and sufficient condition for a code to be instantaneous is that no complete code word be a prefix of some other code word. Next is the construction of instantaneous codes. We'll see this with an example. Encode 5 symbols of a source into binary instantaneous codes. S equal to S1, S2, S3, S4, S5 and X equal to 0, 1. We can assign 0 to S1. Now S2 cannot be set to 1 because prefix property has to be satisfied and we have to form 4 more code words. Then S2 can be assigned 1, 0. Remaining code words should start with the 1, 1. So S3 can be assigned a 1, 1, 0. Now 1, 1, 1 is a 3-bit prefix which is unused. So S4 can be assigned the code word 1, 1, 1, 0 and S5 with the 1, 1, 1, 1. We can see one more method for construction. We have more freedom if we select a 2-bit code word for S1. 4 prefixes are possible 0, 0, 0, 1, 1, 0 and 1, 1. S1 is assigned 0, 0, S2 0, 1, S3 1, 0. Now 1, 1 is the only prefix unused and we have to construct 2 more code words. So S4 can be assigned 1, 1, 0 and S5 1, 1, 1. Next is a craft inequality. The source alphabet S is given as S1, S2 up to SQ and the code alphabet X equal to X1, X2 up to XR. Let the code word lengths of these symbols be L1, L2 up to LQ. Then an instantaneous code for source X is if and only if summation R raised to minus LK less than or equal to 1. This is called as a craft inequality. Assume L1 less than or equal to L2 up to LQ There are only R code symbols, hence R instantaneous codes of length 1 can satisfy the prefix property. Let nk denotes the number of messages encoded into code words of length k. Then n1 will be less than or equal to r. n1 is the number of code words with length equal to 1. The number of instantaneous codes of length 2 must obey the rule n2 less than or equal to r minus n1 into r. This is equal to r square minus n1r. Because the first symbol can be from only r minus n1 remaining symbols not used in forming code words of length 1, and the second symbol can be any of the r symbols. Similarly, we can find n3, and in general nk will be less than or equal to r to the power of k minus n1 r to the power of k minus 1 up to minus nk minus 1 r. Multiplying throughout by r raised to minus k and simplifying, we get summation k equal to 1 to q r to the power of minus lk will be less than or equal to 1. This is the proof of a Kraft inequality. Next is the code efficiency and redundancy. The average length L of the code L equal to summation pi li, where p1, p2 up to pq are the probabilities of the source symbols s1, s2, sq, and l1, l2, lq are the respective code word lengths. The entropy H is equal to summation pk log 1 by pk, and L will be always greater than or equal to HS for a binary codes, and L will be greater than or equal to HRS for a RRE codes, where R is the number of symbols in code alphabet. HRS equal to H of S by log R to the base 2. The coding efficiency is defined as eta equal to H of S by L or HR of S by L. The coding redundancy is R equal to 1 minus eta.